Machine learning can seriously feel like magic, right? This idea of a machine that can think and learn and adapt, it sounds like it's straight out of a movie. But the truth is, it's a lot less like wizardry and a lot more like a really logical, step-by-step process. Today, we're going to pull back that curtain and demystify the whole thing for you.
So, here's how we're going to break it all down. We've got 6 key stages. Think of it like this. We're training a rookie detective to spot a criminal. First, we'll cover how they even learn in the first place. Then, we'll figure out how to choose the right detective for the right case. After that, it's off to the academy for training, followed by a performance review. We'll even look at some common rookie mistakes, and finally, figure out how to build a whole super team of these detectives. All right, let's dive into Section 1, How Machines Learn. Before we even think about building a learning machine, we got to ask a really basic question. How does anything learn? Whether you're talking about a person or a computer, it really boils down to the same core 3-step process. So let's stick with our detective analogy. Imagine you hand a brand new detective this enormous book, just filled with photos of known criminals. Their job? Learn from these photos so they can pick a new criminal out of a crowd. How on earth would they do that? And more to the point, how would a machine tackle that exact same problem?
Well, it really happens in 3 key stages. First up is Step 1, data input. This is simple. You just feed the machine all that data, in this case, all those criminal photos. Then comes the clever part, Step 2, abstraction. The machine doesn't just memorize every single face. That would be useless. Instead, it starts to pick out key features, things like jaw shape or the distance between the eyes. It creates a kind of summary, a blueprint of what a criminal tends to look like. And that blueprint, that's the model. And finally, you get to Step 3, generalization. The machine takes that complex blueprint and boils it down to a simpler set of rules it can use to scan a new crowd. And that's learning in a nutshell. You take data in, you find the patterns, and you create rules to apply to new situations.
Okay, on to Section 2, choosing the right model. So we know how machines learn, but here's the thing. Not all learning tasks are created equal. You wouldn't send the detective who specializes in financial fraud to go investigate a simple robbery, right? Well, it's the same idea here. You have to pick the right kind of model for your specific problem.
And broadly speaking, they come in 2 main flavors. First, you've got your predictive models. Think of this one as your classic Sherlock Holmes. His whole job is to predict a very specific outcome, to point at someone and say guilty or innocent. Then, on the other hand, you have descriptive models. This is more like a criminal profiler. The profiler isn't trying to name a single person. They're looking for hidden patterns, for groups and connections in the data, trying to understand different types of behavior.
So, what does a predictive Sherlock model actually do in the real world? Well, it's all about answering very direct questions like, will my favorite cricket team win or lose the next match? Or, is this credit card transaction a fraud? Or even, what's the price of this house going to be next year? See? Each one asks for a specific, predictable answer.
And what about our descriptive profiler model? This is the one that finds the cool insights you didn't even know you were looking for. It could be something like grouping all your customers into different buckets based on how they shop, or finding clusters of similar-sounding music in a massive library. It can even discover that people who buy milk are also super likely to buy biscuits. That's a classic example of what's called market basket analysis.
All right, Section 3, training your model. We've picked our rookie detective, so now it's time to send them to the academy. The way we train a model is by giving it a big old dataset where we already know all the right answers. Just think of it as a huge stack of solved case files.
Now, the most straightforward way to do this is something called the holdout method. It's super simple. You take all your data and you just split it. Use the biggest piece, say 80% of it, to train the model. This is our detective studying all those old case files. The other 20%, you keep that hidden away. That's the test set. It's like a single final practice exam to see how much they actually learned.
But hold on, what if that one practice exam just happened to be really easy, or maybe really hard? A much more solid approach is K-fold cross-validation. With this method, we split the data into multiple sections, let's say 10 of them, which we call folds. We train the model on 9 of those folds, and then test it on the one that was left out. Then we do it again, and again, 10 times total, using a different fold as the test each time. It's basically like taking 10 different practice exams. This way, you can be sure the detective really gets the material and didn't just get lucky on one test.
Okay, Section 4. Is the model any good? So, our detective has graduated from the academy. They're all trained up and ready to go. But here's the million-dollar question. Are they actually any good at their job? To figure that out, we need a proper, formal way to measure their performance.
And the main tool we use for this is called the confusion matrix. Don't let the name scare you. Just think of it as the detective's official performance report card. It breaks down every prediction into one of 4 buckets. You've got a true positive. Our detective correctly points out a criminal. Awesome. A true negative. They correctly clear an innocent person. Also great. But then you have the mistakes. A false positive. They accuse an innocent person. That's bad. And a false negative. They miss a real criminal and let them walk free. That's also very bad.
So, the most basic way to score this report card is with accuracy. It just asks a simple question. What percentage of the time was the detective right? You just add up all the times they were correct, the true positives and true negatives, and divide by the total number of cases. It's simple, it's useful, but it definitely doesn't tell the whole story.
For that, we need to dig a little deeper. First, there's precision. This asks a really important question. Of all the people our detective accused, how many of them were actually guilty? Having high precision is absolutely crucial when the cost of being wrong, of accusing an innocent person, a false positive, is incredibly high. We need to trust that our detective is reliable.
And then there's its partner, recall, which is sometimes called sensitivity. This flips the question around. It asks, of all the actual criminals that were out there, how many did our detective manage to catch? High recall is critical when the cost of missing a criminal, a false negative, is really severe. Think about airport security or medical screening. You want to be as thorough as humanly possible.
Which brings us to Section 5, Common Model Pitfalls. Because even with the best training in the world, our newly minted detective can still make some classic rookie mistakes. Let's talk about the 2 biggest traps a model can fall into.
First, you have what I like to call the lazy detective. In technical terms, this is underfitting. This model is just too simple. It didn't learn the complex patterns in the data. Its rules are way too basic, like all criminals wear hats. It's so simplistic that it does a terrible job on everything, both the old cases it studied and any new ones it sees. Now, the exact opposite problem is the paranoid detective, or what we call overfitting. This model is way too complex. It didn't just learn the patterns, it basically memorized every single tiny detail from its training data, including all the random noise and weird coincidences. It becomes so obsessed with the past that it can't generalize, and it completely falls apart when it faces a new situation that doesn't look exactly like something it's seen before. And these 2 problems lead us to the bias-variance trade-off, which is honestly the central challenge in all of machine learning. The lazy detective who underfits has high bias. It's biased towards being too simple. The paranoid detective who overfits has high variance. It's way too sensitive and varies wildly with the training data. The trick is, you can't get rid of one without making the other one worse. The entire goal is to find that perfect balance, that sweet spot right in the middle, to build a model that works great on data it's never seen before.
So, for our final section, number 6, making models even better. How do we actually find that sweet spot? How do we take our model from good to great? Well, one of the best ways is to stop relying on a single detective and instead build a whole super team.
There are really 2 main ways you can level up your model. The first is parameter tuning. You can think of this as just giving your single detective better equipment, a stronger magnifying glass, a more advanced forensics kit. You're just tweaking the model's internal settings to make it better. The other, and often more powerful approach, is using ensemble methods. And this is where you stop trying to perfect one detective, and instead, you build a whole team of them.
Ensemble methods are so incredibly powerful because they work by combining a bunch of different, often kind of average models. We call them weak learners, to create one super accurate, strong learner. See, each individual model might have its own flaws or blind spots, but when you put them all together on a team, their different strengths start to cover for each other's weaknesses. It's literally like getting a whole room of detectives to look at a case and then just going with the majority vote. That collective wisdom is almost always going to be better than what any single detective could come up with on their own.
And there you have it. That's how you build a learning machine. We started with the basics of how they learn, then we picked the right type of model, sent it to the academy for training, gave it a performance review, and even learned how to make it better by building a team. We've hopefully taken some of the magic out of it and replaced it with a clear, logical process. Which, of course, leaves us with one last, really big question. Now that we know how to build and improve these learning machines, what's the most important problem we should ask them to solve?